Alrighty guys, welcome to the next video aimed at helping you understand SPSS and statistics a little bit more before your prac exam. So just quickly, before I get into the non-parametric and parametric tests that we'll actually be covering in this video, I want to make sure that everyone understands the correct way to input data if they're given a question that they might have to input their own data for. So I've just grabbed this sample question that I put up in week 8. About a number of university basketball teams performing in the Australian University Championships. So the basis of this experiment is practically you did a study where you had 4 teams perform an agility test. So the thing you're measuring and your dependent variable is agility and your independent variable is university team. And so when we go to write our data into SPSS, you're not going to make each name of the university a variable, which is what a lot of people tend to be doing when they're inputting their own data. So I'll show you what we're going to do instead. So I've got a brand new SPSS file. And so each of my variables in the variable view, everything I write in this name column is another variable. University is a variable. And so is agility score. So I'll just write agility. Now, a lot of people have been doing this. So they'll write UCID as one, Griffith as the next, and then like UAW. That's not actually correct because those aren't individual variables. They're all subsets of the same variable. They're all underneath the umbrella that is university or team. So what I'm actually going to do is code for those in the university row. So I will have university, and then I will go to values. I will click the little ellipse button that comes up there, and then I'll code for my values. So let's make 0 Monash and 1 Griffith. And I'll only input 2 of the data sets for now, just to make it a bit speedier. So selecting what university you're from, that's something you nominate. You say, I'm in the UOW team or I'm in the Monash team. So the input is, the measure is nominal. Agility is something that's measured on a scale. It's not given a rank, it's just a scale. So it's good. So what we're going to do now is input these values all in the same column and then code for what university it is. So I've already done that in this Excel document, so I can just copy and paste it over. And so what we're going to see here is the right way to input your data when you have variables that need to be coded for. Your agility scores all in one column, and then all of these scores are Monash and all of these scores are Griffith. And you can always go back and check to see what you've coded for. 0 is Monash, 1 is Griffith. Alright, so on to the actual content of this video. We will be looking at parametric and non-parametric testing. So I will be showing you each different kind of test and when I do it and why I do it. So the first one I'm going to start off with is a tricky one. It's the chi-squared test. And the only time that you will ever do a chi-squared test is when you have 2 categorical variables. So the second you have a variable like weight or height or BMI, that's all on a numerical continuous scale. That's not going to fall under categorical. If I was going to look at something like gender, which is a nominal variable, so it's categorical, with this variable here falls in previous year, then I could do a chi-square test. Now the reason I can for the falls in previous year is because if we find it in the variable view of the SPSS file, we can see that it's actually coded for in that 0 is no falls and 1 is falls. So the number in this column here does not refer to the actual number of falls a person had. It's just a nomination of whether they fell, yes or no. So that's why it's categorical. So don't get tripped up on that one. So to do a chi-square test, what I'm going to do is go to Analyze, Descriptive Statistics, and Crosstabs. Because I'm looking at gender and falls, I'll put gender in the rows, and then I'll find falls in previous year and put it in the columns. Under the statistics button, I'll make sure I have pressed chi-square, which is the only test we need to worry about. And under cells, I need to make sure that observed is ticked, and it's already ticked, thankfully, and expected is ticked, as well as row, column, and total. After that's done, we'll get our cross tabs, and we'll get this box here. So what we're looking at reporting here, quite simply, is just our Pearson chi-square value, which is 0.023, and our significance, which is 0.879. And what we can see from this is we have a non-significant result. So that tells me that there isn't a significant difference between men and women and the number of people who did or did not fall within those groups. So it means that men did not report more falls than women. So the next test we're going to look at is we'll revisit correlation. So say I ask you to correlate lean tissue mass at baseline with the leg press test at baseline. Now you might be tempted to go straight to our Analyze, Correlate, Bivariate tab and do a Pearson's correlation, but I know that you guys should know at this point that the first thing you need to do is run a normality test. So if we're looking at lean tissue mass baseline and leg press baseline, I'm going to go to Analyze, Descriptive Statistics, and Explore. Get rid of these ones. So what we're looking at is LTM baseline and leg press baseline. Go to plots and make sure normality plots with tests is actually clicked. And we don't need to put anything in our factor list because I'm simply asking if everyone within these two groups is correlated to the other. I'm not asking you to split by gender and I'm not asking you to split by group, so we don't need to put anything in the factor list when we look at normality. So I'll press OK. And here are our tests of normality. Now n is less than 50, so we're looking at the Shapiro-Wilk value. As we can see, we have a significant result for both LTM baseline and leg press baseline. So that means we need to be running a Spearman's correlation rather than a Pearson's. So even if one of these was significant and the other one wasn't, we would still run a Spearman's, because as soon as one variable violates normality, we need to move to non-parametric testing. So now I know I need to do a Spearman's. I'm going to go to Analyze, Correlate, Bivariate, so exactly the same as a Pearson's correlation, except I'm going to do LTM baseline and leg press baseline. And the only thing I have to change is I need to untick Pearson and tick Spearman. That's all. That's the only thing I have to change. Keep two-tailed on. And we'll get our little box here. Now, as we can see, we have an R value, or Spearman's row value, I should say, of 0.716. So that's our correlation coefficient. Then we have a significance of 0.000, which is actually P is less than 0.001. So those are the only two values that you need to report, unless we ask you for the coefficient of determination, which is R squared or rho squared. All you have to do in that case is grab your calculator and square this value. Or if you've forgotten how to get it on SPSS and you like to do it on SPSS better, you can go to Legacy Dialogues and Scatterplot, click Simple Scatter and define that, and we can put LTM baseline against leg press baseline. We can double click on that and we can fit a line, and that will give us our R squared value. It depends what you guys like better. If you prefer to do it on a calculator, that's fine. If you prefer to do it on SPSS, this is the way to do it. What I'm going to do is look at two groups and one variable. So I'm going to see if there's a difference between men and women in the 6 meter usual walk test. Now, to answer that question, I'm going to be doing one of two tests. I'm either going to be doing an independent t-test or a Mann-Whitney U-test, depending on whether or not my data is normal. So to check my normality, I'm going to go to Analyze, Descriptive Statistics, and Explore. in my dependent list, I have 6 meter usual walk, and in my factor list, I have gender. Now, because we're actually looking at differences within gender in our testing, we need to split the in normality as well. Because if we're looking at two separate groups and we want there to be a difference, if we compare the normality in one big group, we might get a result that doesn't actually reflect each group and how their data points are actually distributed. So we need to make sure that they're split. So then I'm going to click plots and make sure that normality plots with tests is clicked and power estimation. You'll notice that if we don't have anything in this factor list, that we can't actually tick this power estimation box, and that's okay. Just make sure that whenever you can do the Levene's test that you are. We're then going to press OK, and here are our results. So we're using a Shapiro-Wilk because our n is less than 50. We have a result greater than 0.05, so this is 0.3 and 0.2, which means that both of these data sets are normally distributed. Our Levene's test is also non-significant, which means our data fits homogeneity of variance. So now to answer the question, is there a difference in the results of the 6 meter usual walk test between men and women? I'm going to do an independent t-test because my data has come back normal. So to do that, we're going to go analyze, compare means, and then independent samples t-test. I'll do this from the beginning. So our test variable, so the thing we're testing, our dependent variable is the 6 meter usual walk. Our grouping variable is gender. And so I'll put gender in this column and then I'll click define groups. And we know that we haven't fulfilled what SPSS needs to do the independent samples t-test at this point because we physically can't click OK and we've got our question marks in our grouping variable. So we click define groups and we put in the values we've coded for gender. So in this SPSS file, 1 and 2 are the codes we've used for male and female. So we need to put in 1 and 2 in our defined groups. Then we can press OK. And here is the result of the t-test. So the things that we're going to report from this test are our degrees of freedom, our t-statistic, and our significance. Straight up from the get-go, look at the significance and determine whether or not this test was significant or not. In this case, p is greater than 0.05, so therefore we do not have a difference in the results of the 6 meter usual walk test at baseline between men and women. I'd then report t, and then in brackets, I'd put 28, because that's our degrees of freedom, equals our t-statistic, which is 1.381. And I then, after doing that, would report the p-value, being p equals 0.178. So now I'm going to ask the question, is there a difference between men and women when we take into account lean tissue mass at baseline? So we'll look at LTM baseline instead of chair rise. So let's do our normality. So we'll go analyze, descriptive statistics, and explore. And instead of 6 meter usual walk, we'll go lean tissue mass at baseline. And we've kept it sorted for men and women because we're looking at the difference in gender again. And we'll make sure normality plots with tests and power estimation is still ticked. And now we can see in our Shapiro-Wilk test that even though our male significance is greater than 0.05, which means all the male data for LTM baseline is normal, the female data is not normally distributed. And because just one of them has violated the test for normality, that means we immediately must move into non-parametric testing. So that means in this case, we'll be doing a Mann-Whitney U-test rather than an independent t-test. So to do this, we'll go analyze, non-parametric tests, legacy dialogues. We're then going to click on 2 independent samples because that's what we have, 2 independent samples. We have men and women. We're going to put LTM baseline in the test variable list, and in the grouping variable, we're going to put gender. It then, like the last screen, asks us to define our groups. So we're going to go 1 and 2 again. And we already have Mann-Whitney U ticked, which is awesome. We can click options to get descriptive statistics if you would like that to be in your output for this question as well. So then we get this output. The only important things we want you to report in this Mann-Whitney U-test is the U statistic, which is 47 in this case, and the significance value, which is P is less than 0.001 in this case. So you could say something like a Mann-Whitney U-test was run as the data was determined to be not normal. It was found that there was a significant difference in lean tissue mass at baseline between men and women. U equals 47, P is less than 0.001, and that's all we'd need you to report. So let's ask a different question. Let's ask if there's a difference in weight between 0 and 12 weeks. So let's ignore 6 weeks. Let's just go between 0 and 12 weeks. Is there a difference between week 0 and week 12 in weight? Now, these are matched data sets because these are the exact same people doing the same things every 0, 6, and 12 weeks. So the same people who got their weight measured at baseline also got their weight measured at 12 weeks. Because it's the same set of subjects, we're either going to be doing a paired t-test or a Wilcoxon-signed rank test. And to determine which one, we're going to do a normality test. And you're going to get very sick of normality tests, but it is absolutely necessary for you guys to understand for your practical exam because it is the thing that determines what test you do. So we don't need to put anything in our factor list because we're just looking at all the people at week 0's weight and all the people at week 12's. So we'll put in weight and then weight at week 12. We'll make sure that plots is clicked, normality plots with tests is selected, and we can press OK. So what we can see here is that weight at week 0 is 0.042 and weight at week 12 is 0.070. So weight at week 12 is normally distributed, but weight at week 0 is not. So that tells me I have to do non-parametric testing. So for this example, I'm going to do a Wilcoxon-signed rank test rather than a paired t-test. So to do that, we'll go Analyze, Non-parametric testing, Legacy dialogues, and we're going to go 2 related samples because that's what we have. We have 2 matched samples. Now I'll get rid of those. So what we're looking at is weight at baseline and weight at week 12. We have our Wilcoxon already ticked, and it will always already be ticked. And what you can also do is click on options and also get your descriptive statistics if you would like it to be output with the rest of the data. So now we'll go down and we get this test statistic box. And all we need you to report for a Wilcoxon-signed rank test is the Z-score and the significance. And so what you could say for this output was, we wanted to see the difference between weight at week 0 and weight at week 12 between all subjects. A normality test determined the data was abnormal. Therefore, we ran a Wilcoxon-signed rank test because we only have 2 time points. We're looking at 0 and 12. Then you could say that no significance was found between week 0 and week 12. Z equals negative 1.159, P equals 0.247. So let's do another one. Let's look at lean tissue mass. So we'll do the normality again, but we're not splitting it this time. So last time we had to split our lean tissue mass because we were looking at it by gender. So let's look at lean tissue mass baseline and lean tissue mass at week 12. We've got normality plots with tests ticked. We can go OK. And so this data is also abnormally distributed. So that to me says I'm going to do exactly the same test. I'm going to be doing a Wilcoxon-signed rank test if I was asked the difference between baseline and week 12. Now let's look at body fat percent. And I know this normality thing is getting boring, but this is how we decide what tests we're going to do. So let's do body fat percent baseline and body fat percent week 12. We know that normality plots is already ticked. And here in our test for normality, we can see that body fat percent at baseline is greater than 0.05, and at week 12 it is also greater than 0.05. So that means this data is normally distributed, unlike lean tissue mass and unlike the other two tests that we've just done. So for this data, if I was to ask the question, what is the difference between all subjects? Is there a difference between all subjects' body fat percent at baseline compared to week 12? So we have the same subjects and we're looking at 2 time points. So this is a paired t-test. So we're going to go analyze, compare means, paired samples t-test. So we're looking at body fat percent baseline and body fat percent week 12. And we can press OK. Now this is the output we're going to get from a paired samples test. The numbers that matter are your significance, your degrees of freedom, and your t-statistic. So straight up I can see that there is a significant difference between body fat at baseline and body fat at week 12, because P is less than 0.001. So to report this, we would say T and then our degrees of freedom in brackets, so 29, equals 5.557, comma, P is less than 0.001. And you can say a paired samples test was run as the data was determined to be normal by a Shapiro-Wilk normality test. It was found that there was a significant difference between body fat percent at baseline and body fat percent week 12. And you would put that output I mentioned before. Alrighty, so if I was to look at 3 variables, so no longer using 2 groups, we're using 3 groups, and I was only looking at 1 variable still, we would either be using a one-way ANOVA or a Kruskal-Wallis test. Now I like to remember that as soon as I have 3 or more groups, I can't use a t-test because t is for 2. So T for 2. If it's a t-test, you cannot do it if there's more than 2. It's only for 2. So I'm going to ask the question, is there a difference in the baseline fat mass scores depending on the group? So remember, our group, we have a low dose, a high dose, and a control group. So we have 3 groups, so we're no longer using 2. So if I wanted to know the difference in fat mass at baseline between those, I'd first need to do a normality test for fat mass at baseline. And because I'm using group in the comparison, I need to use this in the factor list for the normality as well. Plots, normality plots with test is already ticked and power estimation is also ticked. Press OK. And as we can see here, our fat mass baseline for the low group is normally distributed because P is greater than 0.05. Same for the high group, it's greater than 0.05, and same for the control group. So our data is normally distributed, and we satisfy the test for homogeneity of variance, as we have a non-significant result here as well. So that means because I have 3 group and I just want to look at fat mass at baseline, I'm going to do a one-way ANOVA. So to do that, I'm going to go analyze, compare means, and one-way ANOVA. My dependent list is going to have fat mass in it, and then our grouping variable or our factor is our treatment group. Now remember, we need to do a post hoc test if our ANOVA comes out significant. If it's not significant, we don't need to do a post hoc test. Now just to do it all in one go, we need to go to the post hoc button, and to do a post hoc, we're using a Tukey test for the one-way ANOVA. The Tukey test is only used for the one-way ANOVA in this subject. So the only one that uses Tukey is the one-way ANOVA, and you should remember that for your exam. You can press OK. And so here we have our ANOVA output, and when we report an ANOVA output, we need to report our degrees of freedom between groups and within groups, our F statistic, and our significance. So as you can see, we have a non-significant ANOVA result. So that says I should not have done this post hoc test at all. So let's just get rid of it. I just tend to do it all in one go, because if a significant result is pumped out, then I don't have to go back and do the post hoc again. So to report this value, I would need to report F, and then in brackets 2, then a comma, then 41, because that's my degrees of freedom, equals 0.260, because that's my F statistic, and then P equals 0.773. So those are the things I'm reporting. If this value was significant, I would then have to go to the pairwise comparisons and see which ones were significant to each other and report that P value as well. So let's ask another question with 3 groups. Let's look at fat mass at week 12 rather than week baseline. So let's do analyze, descriptive statistics, and explore, and we'll pop in fat mass at week 12. All the right things are ticked. We'll go OK. And here we can see that in the high group for fat mass, we have a significant result, which means that fat mass at week 12 for the high group was not normally distributed. So I have to use non-parametric testing because just one of these groups failed the normality test. So now instead of a one-way ANOVA, I'll be doing a Kruskal-Wallis test. So to do that, I'm going to go Analyze, Non-Parametric Tests, Legacy Dialogues, and we have K independent samples, which just means any number greater than 2. Get these. So I'm going to be using fat mass at week 12, and our grouping variable is group or treatment. Here we also have to define our range. So remember, 1 was the low dose group, 2 was the high dose group, and 3 was the control when we coded. So our range is 1 being the minimum and 3 being the maximum, because those are the values that we've coded for. And this is why we can do more than 2 samples, because this is a range rather than just defining 2 groups. We have the Kruskal-Wallis ticked already, which is good, and we can go to options and click descriptive if we want to. And here's our output. So the only thing you need to worry about from the Kruskal-Wallis test is the chi-square value and the significance. So immediately I see we don't have a significant result, so I can say that a Kruskal-Wallis test was run on fat mass at week 12 over the low, high, and control groups because the data was determined non-normal by a Shapiro-Wilk test. The Kruskal-Wallis test determined there was no significant difference between the low, high, or control groups in fat mass at week 12. Chi-square value equals 0.559, P equals 0.756. Alright, so we covered a lot in this video. So these are the main points I want you to be able to take home after this tutorial. I want you to understand the differences between parametric and non-parametric testing and when we do them. And the big answer to that is when the data isn't normal, we use non-parametric tests. I want you guys to be able to understand the differences between the parametric and non-parametric versions. I need you guys to know which one correlates to which, so which one you do instead of the parametric test. So you will need to know that off by heart. And I need you to understand what values you need to produce in your exam from the output. So I've given a quick summary here about which things you need to report, and hopefully this was helpful for your exam.